Now let's go back to the original class. So today we will talk about the section 2.7, instructions for making decisions. So here, beginning from here, the material is a little bit complex compared with the individual basic operation. So please pay attention to this part, and also you're required to read the corresponding material in your textbook in order to get better understanding. So let's try to think. If we are normal day life, how we can make decision? So basically, we can have two types of decision, right? One is conditional decision, one is unconditional decision. So conditional decision, right? Conditional, unconditional. Conditional means if certain requirements satisfied or condition satisfied, I will do something, right? So for example, if today has a storm and the school might close, right? So that means there's a certain condition that is a storm. So that corresponds to this kind of conditional decision. We have the corresponding statement in our high-level language, right? For example, for loop, while loop, right? And also if, else, and so on. And for the unconditional decision means what? Means there's no decision, you just need to do it. So for example, right? You need to finish your homework. That is no SQ, no exceptional situation, right? Therefore, that is unconditional decision. For corresponding to unconditional decision, we have the corresponding high-level statement, such as a break. Right? As long as you see that, you will jump out of the loop and continue with the next sequence, the continuous statement. Right? So similarly, for our assembly language, we also has, or basically the machine language, we also has the corresponding statement for conditional decision and unconditional decision. Corresponding to conditional decision, we have branch if equal and branch if not equal. Basically means if something is equal, then I will do branch. What mean branch? Branch means I will jump to certain statement or certain operation. If something branch if not equal means if certain condition show something is not equal, I will branch to certain operation. Okay, we will talk about it in detail. If you're confused, don't worry about now. So unconditional decision may have a jump. Okay, so that means I don't care whether there's a certain condition satisfied or not. I always need to jump to certain operation. So that is the corresponding MIP32 machine language or assembly language corresponding to these two ways to make a decision. Okay? So let's just continue to look at our slides. So we talk about conditional decision first. So we just say, right, the corresponding two types, branch if equal, branch if not equal. Let's say the standard format. Standard format is branch if equal, this is the operation, followed by two source operand. First the source operand, second source operand, and then followed by a label. Okay, so what this means is if this operand and this operand are equal, I will branch to the operation which has the label L1. Okay, similarly, branch if not equal, this operation followed by two source operand and then followed by L1. What this mean? Means if the first source operand is not equal to the second source operand, I will jump or branch to the statement or operation with the label L1. Okay, so if I write is a more common way, is you can say is if T1 and T2 are not equal, I will branch to the statement with the label L1, and then you will find which statement has L1. If the statement has L1, is do this way. Then you just do it. So if this is the case, you will directly branch to the instruction which is the addition between S0, T0, and update T3. Similarly, if you do is a branch if not equal, That means you will compare whether T1 and T2 are not equal. If not equal, you will branch to the instruction with the label L1. Okay, I hope this is clear to you. So we just say, right, jump is on conditional branch. That means I don't care whether there's a condition satisfied or not, because there's no condition. As long as I say that, I will directly jump to the instruction with label L1. If you do here, you will see this thing. I will not consider anything. I directly will jump to the instruction with label L1. Basically, as I say this, I will begin to implement this. I don't care whether this one is far from each other or not. I directly will implement this one. I hope this is clear to you. So here, you have to get a better understanding. Let's try to represent assembly language correspond to this high-level language. Okay, so let's try to do that together to get a better understanding. What here say is, I try to check whether I and j are equal or not. If they are equal, I will implement f equal to g plus h. If I and j are not equal, I will implement f equal to g minus h. Okay, so here I'm using a flowchart to represent that. So means I have a condition whether I and j are equal or not. If equal, I will begin with this branch. If not equal, I will continue with this branch. But no matter what, after this, either this one or this one finished, they will continue with the whatever other instruction after this decision-making procedure. Okay? So let's try to do that together to see whether, through doing that together, we can have better understanding. Because the space, limit, I just do this way, you just try to, pretend and not see the solution. Let's just try to do that. Okay, what I do here is I try to decide whether I or j are equal now. So here I can using either branch if not equal or branch if equal, right? Because this means if I and j not equal, I will jump to here. Otherwise, I will continue, right? So also another thing is for normally, as long as you can use in branch if not equal, you will use that rather than branch if equal. It's kind of convention, okay? But it's not always the case. It's just it's a preference. So okay, so let's see. So here, I is what? I is a FG. Let's just list here. F G H I J. So corresponding to S0, what? S1, S2, S3, and S4, okay? So here I will say, if I and j are not equal, right? I and j and S3 and S4. If S3 and S4 are not equal, I will branch to the operation which is subtraction and corresponding to the label else. So I put this. Again, you do not need has to using else. You can using any label to indicate or use as the label of abstraction. I can even using gene here. But as long as you're using gene here, you will need to make sure when you represent this statement, you need to put a gene as a label before that. Okay, so let's just do this, the gene, in case, just to demonstrate it's not has a unique label. Any label will be fine. We will explain why. Okay, so if S3 and S4 are not equal, I will branch to the operation gene. So what the gene is, this label corresponding to the subtraction operation, right? Which is S0 is equal to S1 minus what? S2, right? Okay, so how about the S0, F4 are equal? If they're equal, I will continue to do the addition, right? So I will do the addition. S0 is equal to, I'm sorry, I get a bit confused. Sorry, so here we need to using the assembly language. I confused, sorry for that. So this way, okay? So here will be S0 and which is equal to what? S1 S2, right? S1 plus S2. Okay, so after that means you finish, right? You finish this decision making. As I said, as soon as you finish, you need to make sure you will jump out of this decision making procedure and then continue with the next whatever operation is. Therefore, you need to using jump. If you recall, we said jump means it's unconditional decision making, right? No matter what, as I see that, I will directly jump to the instruction with label axis. So here, so what kind of instruction has axis? I don't care. It's any instruction after this procedure. So this is the overall thing. Let's just recover again. So I try to check whether S3 and S4 are equal or not. If not equal, I will jump or branch to the instruction with label gene. So what is the operation with label gene? It's here, right? So it's a subtraction. And then if they're equal, basically means this one is not satisfied, it's not jump, they will continue with the next instruction. What next instruction is? It's addition, right? Which is here. After that, basically my whole decision making procedure finished, I will jump out of this procedure. So again, I using jump means I don't need to check any condition. I directly can see that I will jump to the instruction with the label axis. Again, you can using other X key value to represent your label. I said I will explain why. We will talk more later when we talk about the corresponding machine language for branch equal, branch not equal. But here I want you to know, because computer only recognize the sequence of binary number. We all know that. They definitely cannot understand this ASCII. Therefore, although here we're using ASCII in assembly language, actually when computer look at that, all it see is a sequence of binary number associated with this label. So what that binary number is, that binary number show or associate with the memory address of the corresponding instruction with this label. Let me say one more time. So although you see the ASCII value here in your assembly language, actually to the computer hardware or the processor, all they see is some binary number associated with the memory address of the instruction having this label. Therefore, you can see I do not, no matter whether I put a gene here, I put axis here, or I put a David here, no matter what, memory address of this instruction will not change. Therefore, it will not influence at all what this operation try to do. Okay, so hopefully it's clear to you. Now let's look at a more complex statement. I want to end in here soon, but I want you to leave something to think by yourself. Okay. So here we just a little bit complex. Just now it's kind of simple for if else. This kind of conditional decision making. Here we're using while loop. Okay, so we say while this safe I is equal to k, then I will do I equal to I plus 1, right? I know I and the k are two high-level variable which store in S3 and S5, and the base address of this array safe is in S6. Okay, so now we try to represent the assembly language corresponding to the high-level language. In today's class, I will represent one more straight way, the assembly language for that. In the slide, they show the other way also. I want to leave this to yourself to think about it, and then we will explain next class. Okay, so how to do that? So first, I need to do the condition judge. I need to know whether safe I is equal to k, right? But before I do this judgment, I need to know where I can find the safe I. This is not safe 1, it's not safe 2, it's a safe I. I is a variable. It's a little bit difficult, right? Because if you recall, before we can say, okay, if I try to do save 2, that is straightforward, right? You can directly using load, right? Like any intermediate register T0, that's it, right? And then 8, right? And what that base address again is a S6. You can directly do so. But the point is now, it's not the safe 2 anymore, it's a safe I. And you cannot just say, I put a here is a 4 times I. It doesn't work that way. Here has to be a constant, right? That is a convention given by the MIPS. So you're not allowed to here to say it's 4 times I, and then parentheses and so on. So how, right? We have to find some way how I still using this kind of representation and properly represent safe I. So here, actually explain how you to do that. So first, I need to calculate 4 times I, right? And then I need to calculate 4 times I, and then plus the base address of safe 0, right? And how you calculate 4 times I? If you recall, we can use a shortcut of shift left logic, right? You try to calculate something times 2 to k is equivalent to do the shift left logic on that thing to the left by k bit. So similarly, if you try to represent 4 times I, means you try to calculate I times 2 to 2. Therefore, you can do shift left logic of this value and then to the left by 2 bit and use that update with some intermediate step and variable, the register, right? Therefore, this first line, what they try to represent is T1 is equal to 4 times I, right? That's exactly what we want to calculate. So now, next we will need to calculate 4 times I plus this. 4 times I is what? It's T1 with this one. This one is S6, right? Therefore, next one, you try to calculate 4 times 4I plus memory address of safe 0. That value will be exactly give you here, right? That means T1 now is equal to 4 times I plus memory address of safe 0, right? So after that, actually I can using load word with a constant here because I try to load the value in T1 plus 0. See one more time. I try to load the value in the memory address of T1 plus 0. T1 plus 0 is what? It is T1, right? So that means I try to load the memory address of this. what is memory address of this? If you read one more time, this is this, right? So that means this instruction try to do is I try to load the value from the memory address of the memory of a safe I. If I load the data from memory address of the memory address of safe I is what? It's safe I, right? Therefore, what I try to do here is I try to load the safe I from their memory address to the register T0. I think this one is not straightforward. I want you to think of that. So basically now I kind of change or revise base address. I revise the base address from memory address of safe 0 to the memory address of safe I. Because of doing so, I'm able to put the constant from outside of the parentheses as a 0. Right? So because T1 already is a memory address of safe I, so now I just want to calculate memory address of I. Therefore, I just put the 0 as a constant outside. So this meet or match the convention of the MIPS 32 for the load word. So therefore, what this one try to do is exactly is T0 is equal to safe I, right? After that straightforward, right? I compare whether safe I is equal to K or not. K is what? K is in safe S5. So I try to calculate whether safe I is equal to K. If not, I will jump outside. If it is, I will increase I, which is S3, by 1. That is why you use an add immediate, right? And then after that, I will go back to the top of the loop and then continue. So I hope it is straightforward. Let me just explain one more time, okay? Let me just try to